Independence Day 2016. Juno arrives at Jupiter and gets to work. The probe angles its high-resolution camera towards this stormy world. Juno's snaps do not disappoint. The images returned from Juno are just beautiful. Suddenly you have this magnificent mosaic of this planet. As a human being, I'm like, oh my gosh, look at this is amazing, this is coming back from Jupiter. These are the closest ever views of Jupiter, a world 500 million miles away. But we didn't send Juno just to take pictures. One of its main goals is to peer deep into Jupiter's dark heart. One of the big questions we have about Jupiter is, does it have a core? And you'd think, well, of course it has a core, like every planet has a core. The Earth has a core, everything does. Well, it turns out Jupiter might not. Knowing what lies at a planet's core allows scientists to wind back the clock billions of years to the formation of the planets. If Juno can reveal what lies deep within Jupiter, it could change our understanding of how the gas giant formed. If Juno finds a solid core, it could mean Jupiter first formed as a rocky planet like Earth, then kept growing. But if Juno finds no core, it could mean that Jupiter skipped the rocky stage and formed straight from a cloud of gas. Answering this question could shine a light on other mysteries too. If we can figure out how Jupiter formed, we can figure out the rest of the story of the solar system. So, how do you probe down into the interior of a planet when all you can really see are the very tops of the clouds? Well, incredibly, you can use gravity. As Juno orbits Jupiter, it can sense in its orbit tiny little variations in the gravitational pull of Jupiter. As Juno speeds around Jupiter, gravitational spikes tug on the craft. Turns out some parts of Jupiter are denser than others. If Jupiter were some solid ball, then as Juno passes by it, as it passes very close above its cloud tops, the trajectory would be very smooth. But in fact, if Jupiter has layers or places where there's more mass and places where there's less, then it's going to pull on Juno a little bit differently. Passing over areas of concentrated mass gives Juno a speed boost. So what they do is the engineers back on Earth can basically just say, how fast is it moving right now? How about now? How about now? And you build up a map of where the mass is in Jupiter underneath the spacecraft as it passes around. Juno's instruments begin to map out the heart of the gas giant, revealing the mysterious core for the first time. What Juno found was this amorphous mass, a fuzzy thing in the center of Jupiter. It's not as solid as we expected if it were just a metal and rock core, but there is something there. In the center of the planet, Juno detects hydrogen and rocky material dissolved and blended together. It's a type of planetary core we've never seen before. Astronomers describe it as fuzzy. We thought we were going to find an avocado, instead we found a bowl of chili. It's a hydrogen fluid chili con carne, so none of our models of the interior of Jupiter turned out to be correct. That means we have to go back to the drawing board. One theory is that Jupiter didn't form from rocks or gas, but from tiny pebbles less than an inch wide strewn across the early solar system 4.6 billion years ago. These pebbles came together. They accreted to form a massive object that was the sort of seed, the core of Jupiter. The swarm of pebbles clumped together to form one giant core 20 times the mass of Earth. But these pebbles can't sustain this growing planet for long. Eventually we need to make a jump from those centimized particles up to really large things like 100 kilometers planet decimals to really kickstart growth of a planet. As Jupiter grows, its appetite becomes insatiable. The cores of other would-be planets are drawn in by its immense pull and absorb on impact, causing Jupiter's core to transform. Huge chunks of incoming rock are mixed up with gas and the pebbles that originally built the core. We think that the core material that might have been there is actually dissolved and mixed in with the rest of the planet. This mix of rock, gas, and pebbles leaves the core in a strange state somewhere between solid and liquid, or in other words, fuzzy. Once Jupiter's core reaches a critical mass, its gravity pulls in all nearby hydrogen gas, building the Jovian atmosphere and leaving the fuzzy core trapped beneath thousands of miles of thick clouds, and that is what formed Jupiter as we know and love it today. Juno's discovery of Jupiter's fuzzy core could rewrite the book on Jupiter's early years, but Juno is just getting started. We haven't even scratched the surface of the number of mysteries there are. There's more to Jupiter than meets the eye. As Juno's instruments begin to reveal a darker side to this giant world, Jupiter's environment is one of the most vicious in the solar system, and that's because of its incredibly strong magnetic field, and Juno is caught right in the middle of it. The gas giant Jupiter holds clues to the mysteries of our solar system. And in 2011, NASA launched a billion-dollar mission to uncover them. 3-2-1 ignition and liftoff of the Atlas V with Juno on a trek to Jupiter. To reach its target, Juno embarks on a 5-year journey. Sending any spacecraft to another planet is going to be tough, but sending one to Jupiter is really pushing things pretty hard. Juno weaves through the solar system with extreme precision. The craft battles violent temperature changes and navigates carefully through the asteroid belt. If there's a fleck of dust in your path and that thing slams into your spacecraft, it can do significant damage. 1.7 billion miles into its mission, Juno finally nears its target. But the probe is hurtling towards Jupiter at 165,000 miles per hour. Juno is moving really fast. It's one of the fastest spacecraft ever. You need to go fast enough to get there, but then you need to be slow enough to be captured by the gravity of that planet. You need to get it just right. Entering orbit around Jupiter is the trickiest part of the mission. Get it wrong, and Juno could slam into the planet or drift out into deep space. To successfully get Juno to enter a stable orbit around Jupiter is almost the same as, say, shooting a basketball from London and having it land on the front of the rim in New York and just sitting there balanced. I could do it. But the red planet, Earth's neighbor, and the destination of NASA's most ambitious mission to date. But this expedition will be harder than we ever thought possible. It hurts to think of how hard it is. It's the farthest a human being has ever been from the Earth. We gotta take every precaution. As NASA's astronauts arrive at Mars, they'll face a huge obstacle. Landing on the planet is a daunting task. In the past, Mars hasn't always rolled out the welcome mat. Mars is kind of like a graveyard for spacecraft. It's actually really hard to send something from Earth and land it on Mars. This is how the European Space Agency hoped its $250 million Schiaparelli lander would touch down in 2016. But the lander systems got it wrong. The parachute detached early, sending the craft into freefall for 33 seconds. Schiaparelli smashed into the surface at 335 mph an hour, leaving a deep black scar on the Martian landscape. It turns out that Mars is actually a particularly difficult planet to land on. Even humanity's most brilliant engineers, we've got about a 50% success rate when it comes to landing on Mars. The red planet is littered with dead spacecraft that didn't stick the landing. And for NASA's first crewed descent to Mars, the space agency must learn from these mistakes. But as the crew hurtles toward the surface, they're battling the same problem as all the landers that failed before. The Martian atmosphere is 100 times thinner than Earth's, so it can't provide the drag needed to slow a spacecraft down. So it's not like the Earth where you can have these big giant parachutes that gently glide you down to the surface. You can use some of the air, but it's hard. The red planet's thin atmosphere is a problem that's been billions of years in the making. Mars doesn't have a large atmosphere because it's constantly being peeled away due to the lack of protection of a magnetic field. The solar wind can strip away an atmosphere. On Earth, a liquid metal core creates a magnetic field which shields the planet and helps maintain the atmosphere. Mars is different. 4.5 billion years ago, Mars and Earth formed from dust and gas in space. Mars forms where building materials were scarce. Its growth was stunted. So Mars is much smaller than the Earth. It's a factor of 10 smaller than the Earth. And that factor of 10 in mass is important. All of that extra mass allows the inside of the Earth to stay warm, and to have a core that's rotating, which generates a magnetic field. 4 billion years ago, the churning heart of Mars started to cool and solidify. And with no hot core, there's no magnetic field being generated. All of the high-velocity charged particles coming from the sun pick away at the atmosphere and slowly tear it away. We know it's losing atmosphere every second, due to the solar wind, so, bye-bye atmosphere. With little Martian atmosphere to work with, NASA had to be creative to get its crewless landers to the Martian surface. In 2012, the revolutionary Sky Crane landed the Curiosity rover using parachutes and retro rockets. Previous missions have used both a parachute and something else like a bouncy ball inflated around the spacecraft. I don't think a human crew is going to be too pleased if they're going to be bouncing onto the surface in an airbag rolling to a stop. Right. To land people on Mars, NASA will need some new tricks. The 2020 rover will overcome the challenge with the Advanced Supersonic Parachute Inflation Research Experiment, ASPIRE. It will rapidly slow down the craft with the force of an airplane jet engine. Music. This is fine for the rover. It's actually going to work no problem, but it's not going to work for people. A human lander will weigh far more than the 2,300 pounds rover. Not even supersonic parachutes could land a crew safely on Mars. NASA will need a new plan. One idea is to use the thin Martian atmosphere in a unique way. There's an idea of coming in really fast, getting to the thick part of the atmosphere and then going horizontal to the ground and gliding and losing your momentum that way. As the astronauts descend, they tilt the nose of the lander towards the Martian surface, aiming for the thickest part of the atmosphere close to the ground. Then they pull up at the last second using friction from the atmosphere to slow the craft. Descent engines switch on for the final touchdown. Is this a crazy idea? I mean, yeah, it's a little bit weird. I don't know if we'd really think about it doing something like this, but I mean, you've got to think outside the box sometimes. Right now, NASA's plans for landing a craft on Mars are still on the drawing board. But even if they can get astronauts onto the surface, the thin atmosphere isn't done with them yet. It causes swirling dust storms that cover the planet's entire surface. Mars doesn't just have dust devils, it has dust hell. And these towering clouds have killed before. When the wind whips up this dust, it can have disastrous consequences. The real problem is just that all these fine particles get lofted into the atmosphere, and it takes a really long time for them to settle back out. And what the dust does is it just gets up in the sky and it sits there and sits there and sits there. As more material gets lifted into the atmosphere, it forms huge dust storms. The storms are so large they block out the sunlight and cool the Martian surface, creating a temperature difference between the ground and atmosphere that causes winds to increase and the storms to grow. And NASA's Opportunity rover knows firsthand the dangers of being trapped in one. Building a planet is no easy feat with many tricky steps along the way. Each one of these steps, going from dust grain to pebbles to planetesimals, takes a certain amount of time. If Jupiter had to wait for distant rocks to collide and fuse, it would take 100 million years to form. And that's not possible because our young sun attacks the gas in the protoplanetary disk. A gas disk around a star can't last forever. The star is igniting and becoming active. The clock is ticking. There's a young star in the middle, and young stars give off violent bursts of radiation, all kinds of solar storms blowing away the cloud. So, if you're going to be a giant planet, you have to move fast. We know our protoplanetary disk only survived for about 4 or 5 million years. So we know that Jupiter was finished forming only 5 million years into solar system history. And that means we have to really jump-start that process and get Jupiter to build a really big rocky core really fast. Jupiter needs a giant core of rock and ice so it can grab nearby gas in the protoplanetary disk. The planet must rapidly build its core and capture this gas before it's blown away. To work out how Jupiter forms faster, we must wind back the clock to the earliest stages of planet formation. So in our protoplanetary disk, we formed our first planetesimals, and we formed these out of all of the little pebbles that are out there in the disk. Now what's still around its neighborhood and everywhere throughout the disk are a huge number of those smaller pebbles. When we add these leftover pebbles to planet formation models, things go a lot faster. Adding these pebbles to the mix, adding this to the models was the big key. These little pebbles can actually supply a lot of mass to these growing protoplanets. That's Pebble accretion, and this is a method of actually accelerating the growth of early protoplanetary cores. Now when a planetesimal forms, it no longer needs another planetesimal to grow, it can feed on the surrounding pebbles. So this planetesimal has some significant gravity, it can start grabbing nearby pebbles and growing by accreting them. And this planetesimal has a huge reach because of how slowly these pebbles are drifting by. So it can reach way out and grab a huge number of pebbles really fast, and that'll enhance its growth rate. And this first planet can grow really fast, eating up all the pebbles around it. It's a feeding frenzy. By gorging themselves on pebbles, planets can grow around 1,000 times faster than with planetesimals alone. But when we use pebbles to model the formation of the solar system, something strange happens.